Hello and welcome. This is a video on breaking down the Ultima series original tile set from the Apple II. The games were made originally on the Apple computers, and the tile sets on there are a little different than how they're done on other machines. But we're not going to get into that too much. That's just how the graphics are designed because of how the Apple II works, the actual bit patterns and such. But the actual layout is roughly the same from machine to machine. We're going to talk about that, how the actual tile set is laid out in memory. Of course, with the Apple II, the biggest consideration, the biggest complication is the arrangement of the rows of the actual graphic, or the lines, if you will, of the actual graphic screen, which are non-sequential in memory. A given line, any given single line in the video memory is 40 bytes wide, and those are sequential. But when you go from like line 0 to line 1, that's in a completely different space in memory. It's not 40 bytes later. I'm not going to get into all of that because that's a very complicated mess, and you should probably take a look at how that's set up to understand what we're going to show here, if you haven't already, if you don't already know how that works. But the basic gist of it is that the most effective way, which we're going to show here, to deal with that is to create a table of the starting addresses of each of those lines that are sequentially numbered. So you actually get the memory address, place it into a table, and then those addresses are sequential from 0 to 191 because there's 192 rows or lines of the graphic screen. And then you can index into that table. You can get sequential rows that way. And we'll break that down, how that's done here. So right now, for the first thing, though, we've got this catalog of the disk. This is the disk that I've been working with, and that I'll be providing. This is already done as far as the tiles are already laid out and placed into these files. So the actual tile data, the graphic tile data, is already set up in the way we're going to show how you can use it with these files. But this also includes the source files. So if somebody wants to mess around with any of the way the sources were made, or to remake them, or whatever you want to do. But this is just a complete disk of all that stuff. So on this disk we have, you can ignore tile test 1. That's just a dummy, or that's just the original file I used to create, or started to work on to create the graphics. That eventually became tile make 1, tile make 2, and tile make 3. And tile make 1 corresponds to the Ultima 3 tile set. Tile make 2 is for the Ultima 4 tile set. Tile make 3 is for the Ultima 5 tile set. The GR files, these .gr files, are the source files. The source files are set up in a way where I had obtained these. Someone in the past had done not really screen rips, but they compiled the tiles onto the graphics screen, and then they were saved. The only problem with this is that they didn't make they only put so many, 100 or so, or 102 tiles per screen, except in the case of Ultima 3 where there's only 64 tiles to begin with. So that's why there's a P1, P2 for these, because this is part 1, part 2, or whatever you want to call it. It's split up. The tile set is split up. We'll see in a minute when it displays on screen how that works. This GR row table is the key table needed. This table is what we'll get into of how we index into what we index into to get the sequential rows on screen. That's already been created, so this holds. I have not actually gone through, and I probably should do it before I put this out. I haven't gone through that entire table. That was one thing I wanted to do, actually, of sequentially going through the table and putting a value on screen to make sure that all of the references are in the right place. So I'll do that before to make sure that the table's right. I'd gotten the table from a graphics programming guide that was published back in the 80s, and it had all the addresses laid out already. So I'm using their format and their way of doing this, which we'll explain in a little bit how that works. It's a very clever and smart way to do it, even if it's not too memory efficient. But they had all of the values already in that table, so I just used them, and that was done with essentially this, where you create. We may as well get into it because this is going to be the key kind of thing. So the way this table is laid out is there are really two tables. And the way I've laid them out in memory is I place them just below the graphics screen memory, which would be hex 2000, 8192 decimal. So I placed them at the two pages, the two hex pages, the two 256 byte pages directly below the screen memory. This is at the top. Essentially becomes not the top. Well, not the top. This is where if you make your AppleSoft program large enough, we'll talk about that in a little bit too. You'd eventually encroach on this area, but that's a whole other thing. So I wanted to have it high enough in memory that it wouldn't get blasted away by something, by the program itself. That's a quirk of the Apple II AppleSoft, and we'll get into that in a second. But we put them in directly below. I did them in high, this page is the high byte, this page is the low byte of all of the addresses, just because that's how they had it laid out in their book. It doesn't really matter a great deal. I suppose you could reverse it if you want to. You just need to know which page is for which thing. And so basically, the way this was done was that I was able to copy all this stuff out and place you'll notice this is basically this entire table, because this table has repeating rows. There's that one and then that one, and then it repeats, and then these two rows repeat, and so I just combine them into one line. Because one thing you can do with the emulator, this made this a lot easier. This is just a little sidelight, is you can actually copy. You can go into the emulator, and you can actually use a Shift Insert key and paste in the text. So that made it tremendously easy to compile the table, because I just went into the monitor, the machine language monitor, machine language monitor, and I just directly enter them into the pages. Because in that monitor you can enter some values, and then you can just hit the colon and then a new set of values, and it will just put them sequentially in memory. So I just did that. Anyway, but that's the table. That's the source table data for the rows. So this is the high byte. So you would take this byte, in BASIC anyway, you would take this byte, multiply times 256, and then you would add whatever the low byte is to derive the row. So this is row 0, row 1, row 2, row 3, row 4, etc., etc. And then you have two separate tables. And the reason for the two separate tables is not so much in BASIC, it doesn't really matter, but in machine language, what this allows you to do is index. So let's say you need to row 4, right? So 0, 1, 2, 3, 4. You need this value, and you subsequently need this value. So by having two separate tables, you can now you just need the address of the tables, and you can basically index using value 4, because you're looking for row 4. You do your indirect kind of get, or either X or Y into this table, comma 4. Right? Well, actually, yeah, you only need two addresses. You just need the high and low byte address. So you get the high byte table, comma 4, and that gives you this value. And then you go to the low byte table, comma 4, and it gives you this value. And you just take those two values and use that to create your row reference address, presumably in 0 page, where you then use the comma Y indirect or whatever to place the value on the screen. Or whatever similar method you want to use. But by using two separate tables, you only need, if these were paired, if this was like 20 and 0, 24 and 0, 28 and 0, you would end up with 384 addresses, not addresses, bytes. And you would not be able to index that with a single byte. By having two separate tables, it's a slight extra step, but you gain the advantage of only having to use you can use the same index value. So once you get your index value of which row you want, you just bang, you get the values and go. It is a little less efficient because you are talking about 256 byte pages. So you're starting at the page boundary on each one. I suppose you don't have to do that, but it's helpful. Doesn't matter as long as you know where you start, what the base address is. But it does leave some bytes open on each table, which I assume if you're doing a machine language, you could find use for. It's 64 bytes or something like that, or around there. So you could probably find a use for 64 or 128 bytes in two 64-byte chunks. I've already got some ideas about that anyway. So this will be the kind of thing. We're going to similarly, eventually, this is kind of not really going to be used this way. We're going to similarly do the same exact methodology for the tile data. Again, this is not in this program that we're going to show you, but for future use in machine language. By using the same methodology, we can also create a table, and this would be the table for the tiles in memory of where each tile starts in memory. So 0, 1, 2, 3, etc., same methodology. And we're going to have to do this a little differently because, possibly for Ultima 5, because Ultima 5 does have 512 tiles. So that really wouldn't work. But for the first 256 tiles, which I believe in Ultima 5 are the only ones that are displayed, I don't think they actually display the later tiles above 256. I believe that those are just animation data and other things that are copied from those memory spaces into the main set. So we're going to predicate on that idea, but certainly for Ultima 4, Ultima 3, and then the first 256 Ultima 5, this method will work. So we do the same thing. We create a table. This is my proposed idea to place them here for testing in BASIC, and maybe even at the end. And we do the same thing. We place a high and a low byte, and then we pre-calculate, because the tiles, which we haven't gotten into yet, so that's a good transition. The tiles are laid out as 2 bytes by 16. So they're 32 bytes per tile. 2 bytes wide, 16 bytes high. And I've approximated that here with the little breaks here to indicate, we've skipped. So we got byte 1 and byte 2. Really it's byte 0. Really should be byte 0 and 1 when you get right down to it. But there's 2 bytes. So anyway. So byte 0 and 1. And then, or at least on row 0, it'd be 0, 1, 2, 3, 4, 5, etc., down to 30 and 31 byte. So because there's 32 bytes per tile, we would then, in this table that we're proposing, pre-calc the multiples, because you don't want to be multiplying while you're trying to pull tile data to spit out to the screen. So we're going to pre-calc that into a table so that we can, similarly, we get our value. Let's say we get a value from the map we're trying to display, and the value is 4, 5, or 6, and then we just index it in a table. That gives us our tile address, and we've got it within a few cycles. So very, very quickly, about as quickly as can be done. A lot of this is predicated on, or the purpose of this, aside from just getting the data and messing with it, is I did want to try some of the goals here for this after getting all of this data sorted out in these tiles. Is one of the goals was to see how fast a routine you could write to get the data to the screen. I have an idea of some unrolled loops and a couple of other things. I'm not sophisticated at this stuff, but I have a couple of ideas that made me think of, well, if you could do this or that or the other thing, you could speed up the process quite a bit. However they did it in the original, it's pretty fast. It's pretty impressive, actually, how quickly they're able to get data up to the screen when they animate. There's obviously a lot of overhead because the game engine has to check for all sorts of factors. Mostly when you move, though, so it's not really so much. But when the screen is just animating while you're like sitting there doing nothing, the update is pretty fast, relatively. Obviously, they're doing things like they're only painting tiles to the screen that are of the animated type. But of course, that still requires a check. You have to go through the buffer. There's a lot of considerations, so of an overhead to do. You have to basically go through the buffer, which, since it's an 11 by 11 screen that you're viewing, is 121 bytes. So you'd have to scan through that 121 bytes and maybe pre-scan it every time you move and create a smaller table. I don't know. I haven't thought about that. Maybe that's the way to do it. Of just the amount of unique animated tiles that exist in that buffer, That's one way I think you could do it. So you kind of, as you move, because every time you move, there's a gap of time that you can do some stuff that you're not really as concerned about how fast you're getting the update to the screen. And there's a bunch of checks that have to be done, obviously. Every time you move, you got to update monsters and blah, 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 blah. But if you're just doing animations that are just animating while you're sitting there paused, or that are animating anyway, in between those times, this is one way to look at it. So there's a lot of stuff like that has to go on. So I'm really doing this as a test just to see how fast I can just spit the graphics out to the screen while doing the animation updates of the tiles that need it to be displayed on screen, and see how fast it's possible to do. And then possibly might work on a AppleSoft program with some machine language to do some kind of tile editor. I'm not really promising that. I'll have to look into that. It's very, very complicated when it comes to this stuff because you're doing a lot of bit flipping that has to be done a certain way because of the unique nature of how the Apple does its graphics. So there's a number of considerations there that other systems don't have. So it could be very complicated to do, and probably a lot easier to do in machine language, but I'll have to do it in AppleSoft because I don't think I have the time to work that all out in machine language. Anywho, those are some of the goals and why we're doing this, aside from just pulling the data and having the data available in some way. All right, so back to the tile set. So we got that tile set. We got our tile set. This is how the tile set works. We're going to pre-calc. Well, eventually, we're not really going to do it in this particular case, but to get the data out, we need, again, our screen table. We've talked about that. I have over here some of the variables the basic program will use, which we'll go over in a little bit. And the trick here is that I didn't realize this until I started working on it, that AppleSoft only uses or recognizes the first two characters of a variable name, at least for regular variables. Well, maybe even for strings, I'm not sure. But for regular variables, numeric variables. So initially I had this, you see this R high, R low. This is the reference to this graphics table location, these two memory locations here. And I originally had that as row high and row low, but because AppleSoft only recognizes the first two characters, they were reading as the same value, the same variable. So that messed me up and I had to rewrite some of the code. Anyway, so just be aware if you're doing AppleSoft that you have that. So I had to write these out to kind of, so I could visually see them all together so I could make sure I wasn't overlapping the first two characters of things. Like this was originally tile IDX and tile ADDR, but again, it read them as the same thing. So because tile ADDR, I already used in a bunch of calculations, and tile IDX was only used in like 2 places, I changed that one. Anyway, so the tile sets now, we get into tile sets. I made a little map here. The way they're broken down, because of how this person constructed them into screens, they are sequential. The tiles are sequential like they need to be, but there are only so many per screenshot, per B save. You basically B saved the screen. And I mapped these out just to make sure I had the right numerical amount, and there's 103 per screen, and then whatever the leftovers at the end. Ultima 3 only has 64 tiles, so they all fit. We're going to show that in a minute. On the disk, then, that's what we got here. These GR files are the source files, as I mentioned before, and then we have U3 tiles set, U4 tiles set, and U5, and you notice the sizes is 10 because there's only 64 tiles, 34, which is a standard 8 kilobyte amount. This is B saving the screen, or not B saving the tiles, but it's 8K of data because it's 256 tiles times 32 bytes, and U5 is 512 tiles, so it's double that, roughly. Okay. And then that's basically it for what's on the disk. The actual, oops. All right, this is the Ultima 3 tile convert. I've already done this, and we'll go over the code here in a second. But the, and I think I'll do it from the other one because there's some differences between the programs. I went ahead and did 3 separate programs too because there were a few differences, like I said, and I wanted to hard code them in and not try to work with some kind of, like I could have said at the beginning, are you using Ultima 3, 4, or 5, and have it do it that way. But really, I did this. This was hacked together a bit. This wasn't meant to be like some kind of real complete kind of creation program. So it's really just something that is, it grew to a tool, and then I just used it in the most obvious way possible by manually changing some of the values to get the final result that I needed, because that's all I really cared about. So I didn't polish this up or make this like you would make a normal program where you would have it truly process like all of the tiles in one go and all this stuff. I had to kind of do things piecemeal. But anyway, this one's set up to actually load the tiles from disk, because this go to at 25 here jumps to a routine that basically was what would let me look at the tiles after they've been saved. So it would basically read them back in from disk and then display them, so I could make sure that what I saved was right. So this is what this is. I've modified this just slightly. So when we run this, we get, so the top part and this little end of catalog text at the bottom is actually the saved screen. That's the screen that was saved for the sources. So whoever created these screens, like you see, laid the tiles out at the top of the screen there up to a certain point, and in this case 64, and later on it'll be 103. This piece is what my program is displaying, and you see if I hit a key, it puts the next one up. Now, interestingly, the way these tiles are laid out, if you look at any other program that does a tile-based system like this of graphics, particularly on, well, I don't know, other than Ultima, I guess, but when you do tile-based stuff like this, You usually have one tile, and it's usually 0. This is the way I've ever done it when I've created these types of engines in the past on the 8-bit machines. Usually tile 0 would be a blank. It would just be a dark square, a blank square, all zeros. And that would be used for blanking out whatever you need to blank out, having an empty space. But the Ultima series, 0 tile is actually a tile of some kind for the most part. Ultima 5, it is kind of it's a weird tile. It's some odd thing that says, that reads as I hacked the map sectors on the Ultima 5 Britannia disc and filled the sector with like 0 to 255. So when you're walking around the world and you get to that spot, you can actually see all the tiles laid out. And that was to make sure the tiles were right. And also I wanted to see what the tile 0 actually was. And in Ultima 5, it reads, when you do a look, where you can look at things, it reads as like a chest of drawers, even though it's just a odd graphic. It's not a blank. Doesn't look like a chest of drawers. The 3 and 4, though, they're some kind of water. So 0 is not a blank. 3, I don't think, used the blanking method in its engine when you play. I think it was 4 and 5 that did that. So I don't know what they're using, or if they're just doing it as if they're doing the blanking method programmatically, or if they're doing it as some other tile that's black in the data set. I'm not sure why you wouldn't use 0, but oh well, they didn't. Anyway, just an oddity. Another oddity here we got to consider as we go through this program of how this is done, because I'm going to go through the code in case anybody wants to, again, mess with this later and kind of give it so you have an idea of how the code works. If you'll notice, well, let me just rip through a few of the tiles real quick here just so you can kind of see. So what this is doing when I'm doing this is now, it has loaded the tile from disk back into the memory space of where, we'll get to that in a second, of where that is, and it is now putting them out to the screen using this graphics row situation to just spit it to this particular spot, So it's getting them sequentially from, the data is sequential, 1, 2, 1, 2, 1, 2, the bytes like we showed over here is laid out like for the tile set is laid out that way. And so that it's, 0, 1, 2, 3, 4, 5 sequential bytes paired in the tile data, but of course to the screen it has to take this row table thing so that they come out sequentially on the screen. Okay, so now if we go here, one thing to note, the screen would fit 20 tiles across because 2 bytes is 40 bytes across, 2 bytes wide, that's 20 tiles. However, because of where these go on screen, how they were designed, they have to go 1 byte over. And that's because there would be a border here. This is for, once we start with Ultima 3, there was now a border, because it has a party and all this other stuff, so there's a border around the entire, play screen. So if you were to take this tile, which I did originally, when I did this display tile, I actually put it to the edge, and all the colors shifted, so it's off. So you have to, with this particular set, and the way these are laid out, you have to be 1 byte in, or at least on the, boundary like that. You can see as you go across, it's fine once they're shifted by 1 byte. But you can't put it at the very edge. If you do, you're going to have to do some kind of shifting of the bits within the tile to get them to the colors come out right. If you were to try to do this, like if you were to try to take this tile set and do like an Ultima 2 screen, that's the entire width of the screen, then you're going to have to do some shifting. As a result, there's only 19 across and then however many rows. So just keep that in mind. When we do our calculations, we have to calculate on a 19 wide line to get, from row to row here of these tiles. Okay, now I have a little routine here that restores my screen. I wrote a couple of little utility screens, or code here. 995, I just can run that and that. Oh, you know what? Do I have that? Oh, there it is, 996. Okay. Anyway, thought there should be an end statement. Anywho, so this is 995 just restores the text screen. 990 is a way to keep track of memory because this is one of the quirks of AppleSoft. So if you look at a memory map of Apple, or the Apple computer, BASIC starts at 800, really 801 hex. And what's curious about that is that it goes up in memory as you write your program without regard for any of the other stuff that's later in the memory. Because when you get down in that area, the text screen number 2, the low res screens, and the high res screens all exist after 800. And there is no check or management in AppleSoft to jump around those memory spaces. So if you write a program that's large enough, it will clobber and knock out all those screens and overwrite those spaces in memory. So in order to use AppleSoft with large programs, I'm not sure how you get above more than about 5K. 5 or 6K, I think, is about the point, which, from 800 to 2000 hex, roughly. So in order to check that, I had made this little code with this little routine just to print this, so I don't have to type it all the time. Because 175, 176 represent the end of your AppleSoft program, with the exception that in AppleSoft, the code starts at 801. For some reason, 800 has to be a 0, and the code starts at 801 hex. I don't know why. It's a quirk of it. But basically, 801, and then up from there, and then that all includes all your code and your non-string variables. But string variables are actually stored as you create them and everything up in memory below whatever the high mem is. So since basic and since DOS is loaded here, that wherever DOS starts, it's below that. It's right below that. So in order to keep track of this, because we know that my table is at 670, 680, and eventually I'll have one at 7168 for the tile data as I do my test later. I know that I don't want to get past that point. So I wrote this code to give me the end of in memory, where my AppleSoft portion of my program ends in the lower memory there, so I can make sure it isn't overwriting that, especially if I'm going to try to do eventually a tile editor. That will be much larger. All right, so on to the code. Now, the way this basic conversion program works is we have, let me get the... that's not quite it. Okay, so this is where we set things up. This isn't entirely used the way I want. The GD string. GS string is your source string, source graphics file name. GD string is your ultimate. Listen to me. What will be the total tile set will be saved as. I didn't actually really use this the way I wanted because you'll see in a minute. But G source is our screen memory. That's HGR1 basically, or HGR, or the high-res graphics screen 1. G destination, we're putting everything into, for our data, this is for our tile data, into high-res 2, page 2, which is 16384 text 4000 hex. So G source is 2000 hex, GDES is 4000 hex. And then we got the table, the split table, the high and the low byte of the graphics row table, as I described before. Then we load in our graphics screen, and this one will get changed, especially for Ultima 4 and 5. Oh, I should probably be doing that on the other program. Actually, load that in. Same process, but just a little bit different. We should actually be looking at this one. It's a little bit more revelatory because the Ultima 3, you can just do it all in one go because there's only 64 tiles. But because we have the split tiles with Ultima here like this, so for 51, so what we would do is as we're iterating through, and again, this is a little on the manual side. I didn't really program this up because I was worried about memory issues. So I just did this the hacked way, P1, to where you have to hack a couple of lines to make it work. All right, so this is now going to load the first Ultima 4 tile. We load that into the main graphics screen, which is where we're going to pull our tiles from. Then we load in also our G-row table. Now in this case, when you do the B loads and B saves, you actually do use the hex values. That's why I've been mentioning them, is because there are hex values involved, even in BASIC for certain things. Not much, but still. Okay. Let's see. We're just going to take a quick look. We want to go to 6020. All right, so this is the Ultima 4 tile set. Now, by the way, this tile piece, I didn't actually calculate where this goes. I just picked, I think, row 100 or something. I wasn't really... I'd forgotten these later tile sets were going to be so much larger. It just happened to work out that it fits there. Anywho, so this is the Ultima 4 tile set, and which technically would fit on this entire screen, although not with the text window down here. You can see there's some animation stuff in here a little bit. Looks like they have 2 frames of animation for many things for some of this stuff. Later in the Ultima 5, there'd be up to 4 frames of animation for certain characters. But you can see here we got a little guy here where the staff is up and the staff is down. So this was an innovation at the time of having animated characters like that. Anywho, so we basically have this character set and a tile set. We're going to go ahead and look at how we derive that then, GB. This is all basically the same as what I talked about just a little bit ago, just changing the source file name. Now, it was necessary to create a variable which doesn't exist in the one for 3, because again, they all fit within one shot, called offset IDX. Offset IDX is what this stands for, off IDX. And this is the tile set offset as you process through the various 1, 2, 3, 4, 5 parts or whatever. So for P1 it would be 0, and because there's 103, when you do 2, it would be 103 or whatever. Yeah, it'd be 103. I wrote these out so that was a little easier to figure out, because you get the whole thing with 0 based, and then you have to figure out, and you can get messed up on this really easy and get these numbers off by 1. So I wrote them out so it was explicit and a little easier to track. But anyway, so 103 would be 2, and then 206 would be when you do the third part, and so on and so forth down for Ultima 5 in a similar manner. So the only thing you have to change when you're processing these, if you were to use this program to create your own sets or whatever from the graphic screens, is you really just have to change this off IDX and take out this 6020, which is not. I'll get to that in a second. Change this off IDX, and then down in the 5000 range, change the GR source file name. This 25 here can be taken out or remmed out, because this is basically a jump to, this sets up, these first couple lines set up the variables and stuff, and then we jump here. This is what does this display, where instead of processing the data, that jump lets me verify, which I think we saw earlier, verify the data by reading it back in. That's where that goes. That's what that is a reference to. So now this is in the thing where it's just flipping through the tiles so you can verify the tiles. Okay, just very important to note that if you try to run this program, it's not going to work until you take that out in terms of making the actual files. Okay, beyond that, once that's taken out, we go sub 6100, which is going to set up our load the tile set. Oops. This is also one you would change after. For the first one, if you were using this program to create these, the first, when you process part 1, you have no tile set saved, or maybe you do, but I didn't have the tile, so this was actually remmed out as well, and then I added it so that it could, because you want to, when you do the subsequent parts, sections, the next 100 tiles, you got to load the tiles in from the disk first, so you want to make sure they're in memory before you add to that set, and then you save it back out. You just repeat that process. Then we basically do a press any key to get started type deal. Okay, now we construct the tiles. This is the tricky bit. All right. So now we're using these XT and YT to basically grid the graphics screen tiles. So we basically go YT 0 to 5. In Ultima 3, it's 0 to 3 because there's not enough rows. I think everything else is 5 rows. And that gets the YT, that's your vertical, tiles. And so this represents a whole tile that we're looking at on screen. And then XT 0 to 18 because there's 19 across. We take IDX, we multiply YT, the rows, times 19, and add XT. This is a pretty standard formula for navigating a table. or any kind of a grid type thing that you're trying to find a particular item you're iterating through. Then we add the off IDX, the offset IDX, because this IDX reference is the reference for the tile where in memory the tile, well, it'll be calculated, but this is the index number, I should say, of the tile that this tile is going to go to in the tile set. Then we go to 4000. And we use that IDX. We add it, we calculate it out, basically IDX times 32 bytes per tile. Multiply that out, add that to the base address of the tile data set, stick that into a variable, tile ADDR. Then we get the row index, and this is where it gets the tricky. This is the whole crux of this, to get this right. So the index, we take YT times 16. So remember, this is where it gets tricky. Remember, on screen, when you're looking at the screen, they're obviously in a sequence. You want to get them in that sequence. But in memory, they're completely different. So we have to index into the table. So we take YT, our row, on-screen row for the tiles, and we multiply times 16 because our table is in order. This table is in sequence of where the addresses are in sequence in memory. Well, the addresses in memory, that would be the sequence on screen. So we multiply times 16 because each tile is 16 rows tall, 16 lines tall, and then we index into the table to get the memory address, basically the starting address for that tile row. So GADDR, we take the high, multiply times 256. Again, this is standard memory type stuff for 8-bit. And then we get the low byte and add it. Okay, now, then we go to 1900. This processes, once we got all the addresses set, this iterates and processes that one tile from the screen into the tile set. Now, it should be pretty obvious how this works from here, but, well, not quite. So since it's 2 bytes wide, once we have the starting byte, we can, we only have to do the 16 rows, because we can pick each byte, because the 2 bytes next to each other are sequential, even on screen. So we only really we don't need to do like an X by Y, we just need the Y. We just need the vertical, the number of the line, which line we're on, and we can pick off the bytes. So again, I got the go sub 4100 here. I guess it wasn't necessary, but well, it was necessary here because it's got to recalculate. So we calculate the index, and then we grab, we add TT to it. Technically, I don't think this was absolutely necessary, but well, yeah, it is because T row index. Well, technically, it wouldn't be. Anyway, this is being more explicit than needed. So we add TT to that row index. This row index, remember, is the row into the graphics row table. We then set that up with the current row address, which is what I just covered. And then we take the XT. Remember, XT is which tile across the row on screen we're looking at, and we multiply times 2. Each tile is 2 bytes wide. That gets us the starting position. However, if you recall, I did say that the very first byte is the screen, on screen, is would be the border. And so they moved it, all the tiles are offset by 1. So you got to then add one more byte to get that offset, so it's shoved over to get the correct starting address for the tile on the graphic screen. Now remember, we're dealing with 2 different data sets here. We're dealing with the on-screen, what the tile looks like and where it is on screen or in the screen memory, and we're dealing with the tile data in the tile set. Tile set's easy because you just go through that basically sequentially every 2 bytes, which is what we do here. We then say, okay, we poke the tile address, tile set data address, TT times 2, because we're pulling 2 bytes per. We're doing 2 different lines here. We're pulling 1 byte here and the second byte here. So we skip, so we multiply times 2 with the peak of our source address. and then we poke blah, 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 all that again, +1 with the peak of that +1 to get the second byte. And then we loop. That gets us our 16 or 32 bytes as we loop through. I also did a little printout here at the bottom, which I had to do after the tile instead of saying processing tile like before, because I don't have these addresses are not, won't be set up until this is done. And this kind of let me keep track just to make sure this looked right, and especially this. I did have it set up at one point where this was pointing entirely to the wrong place. I think because when I had tile ADDR and tile index, and they were using the same variable, and it pulled the wrong data from the graphics row table. Or no, maybe that was the other way around. But anyway, I had something, or no, yeah, it was right. It pulled the wrong it had the wrong value for the tile where it was being stored in the tile memory. So it was completely off. Anywho, okay. I think that's everything up to that point. And there's other support routines here. Yeah. Okay, and then... Oh, hang on. Now, this is the opposite of that routine. Let's see here. So this is the same thing, but in order to display from the tile set onto the screen. And it basically just reverses everything. This T-row index now becomes where we want the one, because we're displaying one tile, as kind of a readback, as a confirmation to look at it from the tile set data. So that's a fixed point on the screen, so I just did 100, row 100 on screen, plus TT. But otherwise, this is the same exact thing. We just now, instead, we poke the screen memory address that we've calculated as, from this, with our tile address data. Poke one byte, poke the second byte. Same thing, just reversed in terms of setting that up. 2100. And then this is the routine that just loops through the tiles to call this routine to display them on screen. You press a key in between, you can hit Q to end. Again, I just add a couple things in there. So this is the actual loop, this is the actual put it on screen kind of thing. And... Okay, this is our save routine, which again, I was going to use that GD string, but I ended up not doing it that way because, I don't know, I just decided to just do it this way. So all of the programs have like all three of these lines. A little wasteful, but basically this is just the B save. And you notice that the links here in hex, 800 for the Ultima 3, because it's only 64 characters, 2000, that's 8K for Ultima 4, and 16K for Ultima 5. I think we already covered 4,000. Yeah, these are the addresses we calculate. That's pretty much it. Yep, that's pretty much it. So if you can follow all of that, then again, if anybody wanted to mess with this program, or at least have some of the base code for how to implement some of this stuff of getting stuff to and from the screen, you've got enough of a base here to work with. In terms of addresses and tile, you can pull the tile data, you pull the addresses, or you have the addresses then for the screen memory, and you have the base tiles you can load, and the row table and all that stuff to mess with. So that's pretty much, I think that's everything. There may be other stuff to cover, but I think that's the core of it. And yeah, so you would just load in whichever tiles set you want, .set. I use that in other, I just use .set wherever I made these types of tile sets anywhere in other projects and stuff in the past. But anyway, naming conventions aside, and you just pull in whichever you want from there. Oh, let's take a quick look. Tile make 3 at Ultima 5. All right, so this is Ultima 5. Oh, this is okay. So this is the last file in the set. This is the end of the 512 tiles. And you can see very likely this is pretty much just animation data of some kind, and or other things. My guess is a lot of this stuff would be copied from here into the main character set for display, or into the main first 256 tiles. So they would, and then that makes sense because you don't need this to be in the displayable characters because they're just animations. You could just take one individual piece here, copy it, because you'd have to do that anyway to animate. You have to update the tile in the set anyway, so they don't really need to be in the first 256. Let me just do a real quick thing here and take a look at the front part of the set here. Yeah. There we go. Okay, so you see now the oddity of that character 0. Now water starts at 1. The first water piece starts at 1 instead of 0, and there's a 0 here with a red square. But this, when you display it, when you actually are in the game, and the 0, you don't see the red square. I'm not sure, it must do something else with it. And it reads as a chest of drawers or something like that. Don't know why. Very strange. But anyway, this is the Ultima 5 tile set. So you can see these are the main kind of displayable, environmental things and things that would need to be put on screen. This is the first 100 and something. And let's see here. We can just, actually, we can quit that. Oops. So we'll go to P3, since this is the end of, let's see here. Yeah. P3 represents tiles 206 to 308. So this will show us where that overlap is. Oh, I did that wrong, didn't I? String equals U5. So somewhere in here, we have the end of our proper, probably right around here, the end of our proper, well, maybe not, let's see, it's 206, 225, yeah, it'd have to be somewhere in here, possibly here, because these look like animation things. You can see there's a bunch of animated stuff and alternate views of things. And some of these, I don't know, maybe some of these, while they're unique and singular, maybe they get copied into another, tile, serve double purposes or something. Another curious thing is that you will see, I can't see it on this one, but if you look at the water here, and some other, well, this is animated, but there are some other, because of the way Ultima 5 did things, this is actually a very curious thing. I noticed this years and years ago. I'd figured this out. I was like, what is that? And then I realized what they were doing. So I think it's got to be in the later sets. Nope. Oh, that's interesting. I wouldn't think that that would be there. Okay. All right. So if you notice these pieces here, at first I was like, what in the world are these pieces or these pieces? And I'm not quite sure why they're in this set, because they're not really displayable technically. But it probably was, well, it probably was for convenience, for indexing. These are masks. What these are for is for things like the river ends and maybe shorelines and stuff, where the water, like the water would flow, like this little piece right here, or whatever it is, would be flowing water in some way. So when you animate the water and the water tile gets, moved down one line for the animation, and then if there's one of these pieces on screen, it grabs whichever piece it is and whichever corresponding mask it is, and it does an XOR. and then everything gets masked out except for the water. This then lets the water show through, and the rest stays of whatever's in the tile. It's a very clever method for this time frame. This is 85 or 87. Very clever way of pulling that off in an 8-bit situation without using, well, and being able to animate things like that. So there's masks in here in some cases for this sort of stuff. Very clever design. Anyway, I thought that was interesting. But so this is the middle 103 to 205 characters of Ultima 5. So anyway, so that's our presentation, or whatever you want to call it. And hopefully that will help people figure out things they can, or if you want to do anything with the Ultima character sets. But I had not been able to find. I did this because I had not been able to find the character sets by themselves in what we would call a standard format for tiles, and that's that 2 bytes wide, 16 bytes tall, or however whatever way you'd make a tile set. But in this case, that's how they're made, and laid out as sequential a sequential tile set in memory. So this way, this standardizes them, gets them into a standard format that then could be used to make or modify or whatever people might want to do. I wasn't able to find that anywhere. There's actually very little information on how this stuff was designed, even figuring out those masking things. I don't know if anybody really ever, there's even an article that talks about it anywhere, maybe somewhere in the past, but I just figured it out back in the day on my own, and through deduction of how they were, because I was like, how are they doing this animation, for the river, the ends of the rivers, which are narrow and tapered, and the grass stays put and the water's moving. I thought that's a clever effect, and then I saw that stuff and realized they were using a masking method. So stuff like that, there's a lot of this technology that people just don't know these days how that was done. This would give people a chance to kind of experiment with that now that the data is kind of available in a fairly standard format, and with all the other tools for doing having the graphics row tables set up already. So hopefully these tools will help people if they want to mess around with this stuff in the future.